Welcome back for our next lecture on electrochemistry. Last time we started with a discussion about one of the most ancient and primitive reactions ever to occur on the Earth, the dissolution of metallic iron into the new oceans of our fledgling planet. We discussed how it was all about exchange of electrons and how the differing affinity for them can cause one material to accept electrons from another, a process responsible for the iron-rich chemistry of early oceans. Today we're going to bring that class of reactions into the human age. Today we're going to take a step toward understanding how humankind came to understand how and why electrons flow from one substance to the other. It'll be another building block towards understanding how modern engineering gives us corrosion-free metals, batteries with stunning electrical storage capacity, and panels that convert energy from the sun into electrical potential. Last time, we discussed redox reactions and how we can combine the half-reaction potentials to determine the EMF potential for any given redox reaction. That is a useful value, but the benchmark for reaction spontaneity isn't usually voltage, it's free energy. And this lecture is dedicated to bringing redox reactions into the fold and connecting EMF with free energy. So we know that positive EMF means a redox reaction will proceed. But just how spontaneous is that reaction? Well, we'll see very soon that the real usefulness of redox reactions in chemistry and engineering is not simply knowing if they will progress, but how much chemical energy is released when they do. This quest will introduce us to three of the greatest chemical minds in human history. It starts with the story of a young theoretical physicist named Robert Millikan. Millikan was working at the University of Chicago in the first decade of the 1900s and had made it his personal quest to determine the charge on a single electron. Now, knowing that that value is going to be critical to someday unlocking the secrets of electrochemical reactions, he wanted to know that number. But how can that be done? A single electron is far too small to isolate using the technology that was available to Millikan over a century ago. Yet he did succeed in getting his measurement. He did so with remarkable accuracy. Now, Millikan was able to get this value using a device that suspends charged oil droplets in magnetic fields. In this ingenious experiment, Millikan generated droplets of oil by spraying them through a very small nozzle into a vacuum. Once these droplets were free from the nozzle, of course, gravity was free to act on them, pulling them downward into a second chamber. In this second chamber, Millikan used an X-ray beam to ionize the droplets, and this gave them a negative charge. So these oil droplets now had varying degrees of negative charge. Some may have picked up only a few electrons. Others may have picked up many, many electrons. Now, Millikan had no idea how many each droplet picked up. This, of course, might seem like an obstacle, but remember that electrons are incredibly small compared to the mass of atomic nuclei. So adding electrons to these oil droplets should not appreciably change the mass of each droplet. Of course, at this point in the experiment, droplets would simply continue to fall through to the second chamber. But for one factor, the second chamber contained two electrodes, one above and one below. With the electrodes off, there was no electromagnetic field in that chamber, so droplets indeed simply fell right on through at a velocity consistent with their mass. But when the electrodes were turned on and began to generate a positive charge in the top and a negative charge on the bottom of the vessel, something remarkable happened. The speed of the falling droplets began to slow, as the negative charge at the base repelled the oil droplets and the positively charged plate at the top of the chamber attracted them. Now, by setting the charge separation carefully and measuring the exact field strength needed to levitate a given oil droplet, Millikan could calculate the total charge on that droplet. So how did this help him measure the charge on a single electron? After all, the droplets had many, many electrons giving them their charge. Now, the secret lies in the same logic used by Dalton to prove his atomic theory a century earlier: multiple proportions. Millikan repeated his experiment many, many times, and all of the total droplet charges that Millikan measured were whole number multiples of one very, very small number. This number, 1.6 times 10 to the minus 19 coulombs, is the charge on just one single indivisible electron. It was an ingenious way to elucidate the charge of a single particle, far, far too small to isolate using the technology available at the time. And so ingenious was this tiny little number that it won Millikan one very big Nobel Prize in Physics in 1923, some 50 years before technology would allow us to actually isolate a single electron for study. So, Millikan had successfully determined the charge on an individual electron. Make no mistake, this was an extremely valuable measurement in and of itself. But in the world of chemistry and physics, a different value has become the most commonly used for reporting the charge on electrons. And that's the charge not on a single electron, but on a mole of electrons. Remember that when we look at reactions, and particularly the coefficients on reactions, we usually mean moles, not individual atoms or molecules. So by multiplying Millikan's charge by a mole, we get 96,485 coulombs per mole of electrons. Now this value is incredibly useful in the quest to tie electron motive force to free energy. And we named this value Faraday's constant in honor of Michael Faraday, one of the original electrochemists who started us on our way to understanding how the flow of electrons is tied to chemical free energy. Faraday is actually widely regarded as the father of modern electromagnetism. Michael Faraday came from humble beginnings. Born in England to a blue-collar family, Faraday had the fortune of being offered an apprenticeship with a local bookmaker. And during his 7-year apprenticeship, Faraday learned the art of bookmaking. But he took something far more valuable than that. Faraday's love affair with books as a young man turned out to be not with making them, but with reading them. His apprenticeship exposed him to many works that someone of his birth status might have otherwise never seen. And Faraday seized that opportunity. It's widely believed that his reading during his teenage years is what inspired him to attend lectures by none other than the revered Humphrey Davy. As the story goes, Faraday took detailed notes of Davy's lectures, about 300 pages worth, which he then sent to Davy in a letter. Faraday's obviously deep and abiding interest in chemistry caught Davy's attention, leading Davy to offer him an assistantship in his laboratory. Now, Faraday's life was forever changed. This is because Davy was one of the first electrochemists. He was one of the first to use electrical current to induce chemical reactions, and we'll investigate some of his work in our next lecture. When we consider how electrical currents generated, we'll talk about Davy more, but for now I just want to mention him because he very clearly influenced Faraday's interest. For part of his career, Faraday continued some of Davy's work, and he drew a correlation between the amount of a reagent that could be oxidized or reduced when a specific amount of current was applied to it. He found that increasing the current, or amount of electrons flowing into or out of a substance, increased the amount of that substance that was reduced or oxidized, respectively. Now, although Faraday's career predates Millikan's, the contribution of Faraday to electrochemistry prompted Millikan and others to name the molar charge of electrons Faraday's constant in his honor. So the big deal about Faraday's constant is that it allows us to relate the free energy change to the electromotive force for any given reaction. And it helps us using an equation that reconciles both the issues of sign and the issue of the stoichiometry, or the coefficients in a reaction. Let me show you that equation now. It looks pretty simple, doesn't it? And it is pretty simple. Delta G naught, that's the free energy change for any redox reaction, is equal to a number equal to minus the total number of electrons exchanged in the process times the Faraday constant times E naught, which is the EMF at standard conditions as well. So the Faraday constant gives us a way to get back and forth between the electrochemical world and the free energy world. So we have free energy equals moles of electrons times Faraday's constant times the cell potential, in this case under standard conditions. Now, we've already determined from our previous calculation that the overall EMF for the dissolution of iron into acidic aqueous solution under standard conditions has a potential of plus 0.440 volts. And if it's my need to get out of this electrochemical terminology and into free energy, I now have the tools I need to do so. All I have to do is insert 2 moles of electrons. Remember, we determined when we broke this into half reactions that we have 2 moles of electrons being transferred as the reaction takes place. So we now have something here that accounts for that. Next, we have Faraday's constant, the charge on a mole of electrons, 96,485 to be exact, and the cell potential that we determined previously by breaking the overall redox reaction down into reduction and oxidation half reactions and then summing the potential for the two. When I place this number in, notice that my calculation gives me a unit of Coulomb volts. That's an interesting unit, isn't it? But a quick run to your text will reassure you that a Coulomb volt is equal to a joule. Sure. So this gives me a way to determine the overall free energy change in the redox process. All I need to know is the cell potential and the number of electrons that are exchanged during that redox process. So far, we've met 2 of the founding fathers of modern electrochemistry. The first is Millikan, who followed in the footsteps of J.J. Thomson, very accurately determining the charge of Thomson's electron using oil droplets. The second is a familiar name, Michael Faraday, who first related the amount of current to the amount of reacting material in electrochemical reactions. Millikan's electron charge was used to craft an equation that relates the standard redox potential of any reaction to its standard free energy, an equation that uses a constant named in honor of Faraday using Millikan's results. But to finish our story for today, we're going to need to visit one more great scientist. Our third patriarch hails from Germany. His name was Walther Nernst. Nernst was a well-established researcher in the German system in the early 1900s, but he was more than that. He was an inventor. Nernst had already created a special lamp that used ceramic filaments to generate light, a significant improvement over the carbon-based lamp used by famed American inventor Thomas Edison. Having bested Edison's design, Nernst became a wealthy and revered scientist. And with wealth and recognition come opportunities. Opportunities to pursue whatever problems you want to solve. And Nernst had one in mind. Nernst was a consummate electrochemist. Devices like his lamp relied on the flow of electricity to operate. Now, electricity is simply electrons flowing through wires or other conductive media. Just like in chemical reactions, the electrons have to come from somewhere and they have to have a destination. But so far, the Faraday constant has only allowed the free energy to be calculated for processes under standard conditions. That's room temperature, 25 degrees centigrade, and concentrations of 1 molar reagents for all the species involved. Now, that's more than a bit limiting, and Nernst was a man of practicality. Now, what if we could vary the concentrations of reactants and products in electrochemical reactions? If so, then the EMF should change. Faraday's equation didn't account for this, and Nernst wanted an equation for all occasions, but there wasn't one. So, he came up with one. Before we get to the Nernst equation, I'd like to show you an example of an electrochemical cell, a very special kind. Now, in electrochemical cells, we separate half reactions. So far, we've only thought about half reactions as taking place right alongside one another within the same mixture. But part of what makes the Nernst equation so useful and valuable is that we can apply it to these electrochemical cells as well. So they're worth taking a look at. Let's consider this reaction, the reaction between zinc metal and copper 2+ ions in solution. If I go to my reduction cell potential table, I can determine these values right here just from reading them from the table. The reduction potential for copper is plus 0.34 volts. The reduction potential for zinc is minus 0.76 volts. And because, in this case, zinc is the one being oxidized, I have to remember to reverse the sign on that potential. And when I do, I determine that the overall cell potential is 1.10 volts at standard conditions. That means 1 molar of all reagents. So let's think about what happens if instead of running the reaction all in one pot, I take 2 pots. Let's take 2 containers here and fill them with different solutions. One solution will be 1 molar zinc nitrate. The other solution, 1 molar copper nitrate. Well, they can't do much right now, can they? Because they're not in contact with one another. But first, let's put a plate of zinc into our zinc solution. Let's put a plate of copper into our copper solution. Now, I've labeled these as electrodes, and I've also given them special labels as anode and cathode, and we'll talk about that in just a moment. But again, no reaction can happen yet. But when I connect the two with a wire, electrons have the ability to flow from one cell into the other. So a redox reaction can take place in which the reduction and oxidation are happening at different locations, but are still connected by a medium through which those electrons can flow. So let's put a voltmeter in there and see what happens. Now we know that there is a positive 1.10 volt potential, right, that's pushing this reaction in favor of having zinc ions form here and having solid copper form here. So what would you expect to happen in this situation? Right, of course, we're going to have one of our zinc atoms here become a zinc ion, liberating 2 electrons, which will create an electrical potential. And as it reaches the other electrode, it's going to reduce the copper down to copper metal. But there's a problem here, right? If I want to continue this reaction, I need to do something because my electrons aren't moving anymore, right? It's already stopped. What's happened? Well, what's happened is those electrons came over here to reduce the copper, but then charge built up. You'll notice here I have fewer copper ions and still all of my nitrates. Over here I've added zinc 2+ ions, but no nitrates. So very, very quickly, that electrical current is going to stop, right, in response to that charge buildup. I need one more design element. That design element is something called a salt bridge. And a salt bridge simply allows different charged ions to migrate back and forth between the 2 cells while not allowing the primary constituents of my solutions, my copper and zinc ions, to move. In this case of a salt bridge here, notice that my sodium ions move over here to balance the charge in my cathode cell, and the nitrate ions move to balance the charge in my anode cell. Now the anode is the location where the oxidation reaction takes place, and the cathode is the location where the reduction takes place. These are terms that it's very good to be familiar with because we often will refer to them in this way. Now additionally, we will depict cells like this sometimes using a kind of shorthand notation. And in that shorthand notation, we place the anode reaction first, showing the solid material and the ions it's creating, separated by a single line. That single line tells me that they can react and touch one another. Then, of course, we have our cathode, right? We have our copper 2+ and copper solid reacting at the cathode, separated by a single line to let me know they can interconvert. And they're separated in the middle by a double line, telling me that those 2 cells are separated from one another and cannot cross over and react directly. So you may see this type of notation used to depict what an electrochemical cell looks like. So now we're ready to really think about the Nernst equation and how it's applied and how useful it can be. And this is it. The Nernst equation relates the standard EMF for a reaction to the EMF at any conditions that we can imagine, right? Including changes in temperature and also changes in concentration of the reactants. There's a natural log in here, and oftentimes I'll work directly in natural logs. But you may also often see the Nernst equation written in a log base 10 format. And to do that, we simply have to add a factor of 2.303 to the pre-log term. So this is actually one of the more preferred forms, and I'm going to work with this one today. But either one of these are mathematically equal and will get you the same result, as long as you're very careful to either use your pre-logarithmic factor or use the natural log. So let's use the Nernst equation now to determine the cell EMF at a non-standard condition. So for this, we can't go to a table necessarily. We'll still go to a table to get our E0, right, to get our standard cell potential. But we have to actually calculate the potential under our non-standard conditions. And here are some non-standard conditions. So what is the EMF or cell potential for the reaction at 298 kelvins, standard temperature, in which an anode is zinc metal in a solution of 1.9 molar zinc nitrate, and the cathode is copper metal in a solution of 0.1 molar copper 2 nitrate. So we're no longer at 1 molar. So our originally calculated EMF is not going to be valid anymore. We've got to compensate for this. So here's our reaction and the Nernst equation. Now, we know from our previous calculation that E naught is 1.10 volts positive. We also know from the reaction that the reaction quotient is copper ions divided by zinc ions. Now, I can leave out my solid copper and my solid zinc because the concentration of a pure solid never changes. So it will never have an impact on that equilibrium. And this is a standard rule for heterogeneous equilibria like this. We've got a few more pieces of information here. We know R. We can get that from any table. We know the temperature, it's been specified. We know the Faraday constant because Millikan helped us determine it. And because we broke our reaction down into half reactions, I'm sure you did, we know that 2 electrons are transferred during this particular process. These are all the values that we need to apply the Nernst equation. So when we put these values into the Nernst equation, it simplifies down to something like this. This is 0.0592 over 2 volts times the log of my reaction quotient Q. That will give me the quantity that I need to either add or subtract to the standard EMF to figure out exactly what the non-standard EMF for my particular cell is. So let's apply that. In this case, I was specified as having a 0.1 molar solution of copper 2 and a 1.9 molar solution of zinc 2+. So in this case, my new cell voltage is 1.06 volts, somewhat lower than the standard cell voltage. And this should make some sense to you, right? Because in this case, the copper concentration was already fairly low and the zinc fairly high. And if we continue this process going higher and higher, let's say that we have a ratio that's 0.01 to 1.99, my cell potential goes down. If I go even farther, let's say 0.001 molar zinc, now my cell potential has dropped even further. And as these begin to approach equilibrium, the cell potentials will continue to drop. And this is the effect that you see as your battery slowly dies. You're seeing these non-equilibrium conditions taking over and driving the voltage in that particular reaction. This kind of electrochemical cell, one in which we have copper and zinc reacting, is sometimes also called a Daniell cell. And we're going to build one right now here in the lab. To do this, I've got a 1 molar solution of copper 2 sulfate and a 1 molar solution of zinc sulfate. So we're going to be building this using concentrations that should give us the standard EMF for the cell when we measure it using our voltmeter. I'm also going to use, of course, a zinc electrode. That's going to be my anode where oxidation occurs. And I've got a plate of copper here. That's going to be my cathode where reduction will take place. So let's get busy building our Daniell cell. Now to do this, I'm going to place, again, first my copper cathode into the copper solution. Next, I'm going to place my zinc anode into the solution of zinc sulfate. And of course, if we're going to have an electrochemical cell, we have to connect them, which I'll be doing through a voltmeter, which will display a voltage right here on the display. So let's go ahead and hook up that zinc anode. There we go. Try to keep my wires out of the way here. And let's connect that copper cathode. And what do we see? Well, we see about 10 millivolts of potential. Not what we anticipated, right? But remember, we've already discussed this. We can't have current flow one way without ions flowing the other to balance the charge. And for that purpose, I have a salt bridge. And this salt bridge consists of a solution of sodium nitrate. And it's going to provide the ions that will flow to balance out the charge change as the electricity flows from one half cell to the other. So let's place that in there and see if that affects the EMF of the cell that I've built. How about that? So now that we've built our Daniell cell, we can see that the voltage that's generated by our 1 molar solutions of zinc and copper is 1.11 volts. Exactly what we predicted when we calculated the standard EMF for this type of redox reaction. But we also used the Nernst equation and determined that if we changed the relative concentrations of zinc and copper ions in the two half cells, that we could manipulate the voltage a little bit. So let's put Nernst's equation to the test. So I've made a small change to my cell here. At the moment, what I did was I just removed some of that copper solution, but it's still a 1 molar copper solution, so my voltage is still reading at 1.11, or at least that's what it rounds to. That, again, is the standard EMF for a Daniell cell. But to test the Nernst equation, we're going to dilute that copper solution, which is why I've removed so much of it. When I add this water and dilute that copper solution 20-fold, we should see a slight reduction in the EMF for this particular electrochemical reaction. So let's add it now and see what happens. All right, not quite as pronounced as I'd hoped to see, but we definitely see a reduction in the overall EMF for the cell because we're no longer at standard conditions. And we have to use the Nernst equation to be sure that we model these kinds of changes in cells that don't have exactly 1 molar solutions in each of the 2 half cells. So here we have a very subtle but very real proof that the Nernst equation works. So in this lecture, we met 3 great electrochemical minds: Millikan, Faraday, and Nernst. We started with Millikan, who created a now famous experiment in which charged oil droplets were suspended in an electrical field to measure their charge. We saw how he discovered that all measured charges were integer multiples of one number, 1.6 times 10 to the minus 19th coulombs, and how this number is in fact the charge of a single electron. Next, we were reintroduced to a familiar scientist, Michael Faraday, who's the namesake for Millikan's electron charge multiplied by a mole. This so-called Faraday's constant is the charge on 1 mole of electrons, and we saw how this number can be used in conjunction with the number of electrons exchanged in a reaction to relate the standard redox potential to the standard free energy of the reaction, a monumental theoretical breakthrough. Then we made the acquaintance of one Walther Nernst. This prolific inventor and man of action took the empirical value obtained by Millikan and the fundamental relationship between free energy and electrical potential discovered by Faraday and blew the lid off of electrochemistry by formulating an equation that allows us to relate redox potential to the free energy change under any set of temperature or concentration conditions that we can imagine. Next time, we're going to do just that. We're going to see how the work of Millikan, Faraday, and Nernst has been applied to a host of electrical technologies that we use every day. From the battery that starts your car, to the high-fidelity speaker connections in your stereo, to the tools that physicians use and even implant in their patients. Electrochemistry touches all of our lives in multiple ways. Our next lecture is going to honor that fact as we explore some of the remarkable applications of the work of these 3 men. Now that we've completed our lecture content on how to link the EMF of a reaction with free energy, let's go back and look at a problem that we discussed previously in another challenge question. Let's think again about copper cementation using metallic iron. Just as a refresher here, remember we considered the process here in which a solution of copper-2 ions could be precipitated, right, those ions at least, could be precipitated using solid iron because we knew the activity series predicted it, and we were even able to calculate the exact electromotive force that was driving this reaction forward, causing some of the iron to dissolve and most or all of the copper to precipitate as a solid which could be recollected. So our next order of business is to get ourselves into the realm of free energy for this equation. Now, here's our question for this particular lecture. Knowing that the standard electromotive force for this reaction is plus 0.78 volts, which we determined previously, what is the standard Gibbs free energy for the reaction? Right, so we need to traverse that barrier between voltages and free energies, and we're going to do that now. So again, here's our reaction. Copper-2 plus solid iron becomes copper solid and iron-2 ions. And we determined that the voltage was plus 0.78 under standard conditions. That's 1 molar reagents. So here are the half reactions that we determined, and now the half reactions are going to be particularly important, not just because they allow us to determine what the oxidizing and reducing agents are and which of these species are oxidized and reduced, but because they tell us exactly how many electrons are exchanged. And that is critical to calculating the correct free energy change for the process. We have to acknowledge that during the reaction, as written, 2 moles of electrons are exchanged between the oxidizing and reducing agents. So, with that knowledge in hand, let's convert this voltage into a free energy. We're going to use our equation. Delta G naught is equal to minus N times F times E naught, or the standard EMF for the reaction. So to get that free energy, we're going to use N, which we just determined is 2, because 2 electrons are exchanged. So in this case, we're going to use 2 moles of electrons as our value for N. Putting this equation to use, my free energy is equal to minus 2 moles of electrons, which I was able to determine using the half reactions for this particular redox reaction, times Faraday's constant, 96,485 coulomb per mole of electrons. Remember, this was taken from the charge on electrons measured by Millikan and then named in honor of Faraday, one of the original electrochemists. And my calculated EMF for this particular reaction, plus 0.78 volts. So when I run this calculation, I should get a value that tells me what the Gibbs free energy change is for the same reaction that we previously discussed in terms of electromotive force. My unit analysis tells me that moles of electrons will cancel, and I'll get an answer in units of coulomb volts. Now remember, a coulomb volt is also equal to a joule. So when I run my calculation, I get negative 1.505 times 10 to the 5th coulomb volts, which is equal to negative 1.505 times 10 to the 5th joules. This is a fairly powerful downhill energetic driving force, and one of the reasons why this reaction works so well and is used so commonly to recover the more valuable copper ions from effluent solutions in industrial settings at the cost of having to dissolve just a little bit of relatively inexpensive iron metal.